If your day is done and your mind is loud, breathe once and let it soften. Tonight we will wander slowly through space, one gentle fact at a time, until the cosmos feels like a familiar humming blanket. There is nothing you must do now but listen. Let your shoulders loosen, let your thoughts find a rhythm like the slow turning of a planet, and allow these small truths about the universe to settle around you like cool moonlight. If these quiet journeys help you rest, consider liking or subscribing so others can find this place of calm. Fact 1. The universe began in a hot, dense expansion, often called the Big Bang. More than about 13.8 billion years ago, space itself stretched and cooled, and the initial fireball smoothed into the first atoms. Imagine that first light like a dawn expanding across all directions. Let that long-ago warmth fade into the background as everything slows. Fact 2. During the first tiny fraction of a second, the universe likely went through a phase called inflation. Inflation is a rapid stretching that smoothed tiny wrinkles into vast, gentle curves. Those microscopic fluctuations are the seeds that would one day become galaxies. Picture a small ripple becoming a broad, soft wave across a calm sea. Fact 3. The cosmic microwave background is an echo of the early universe's light. About 380,000 years after the beginning, the universe cooled enough for electrons and protons to combine into neutral atoms, letting light travel freely. That faint glow still fills the sky as a cool microwave hum we can measure. Imagine a distant, diffused warmth pressing gently at the edge of everything. Fact 4. That background glow carries tiny temperature differences called primordial ripples. Those ripples are variations in density that grew under gravity into the large-scale structures we see today. They are like faint texture in a woven blanket that later became galaxies and clusters. Let the pattern feel steady and old, as if stitched long before your birth. Fact 5. The observable universe has a radius of roughly 46 billion light-years. Although the universe is about 13.8 billion years old, expansion stretches the distance that light has traveled, so the sphere we can see reaches far beyond the age times speed of light's simple estimate. Think of it as a gentle horizon you can look toward but never touch. Fact 6. There may be no meaningful before the Big Bang in the way we think by time. Time itself appears to be a property of the expanding universe, so asking what came before can be like asking what is north of the North Pole. Some theories imagine prior phases. Others treat the beginning as the earliest meaningful moment. Let the question soften rather than demand an answer. Fact 7. Quantum fluctuations in the earliest moments may have seeded everything we now call structure.
On the smallest scales, particles and fields spontaneously vary. When inflation stretched those tiny differences wide, they became the blueprint for galaxies and voids. Picture tiny sparks blown out into a slow, intricate pattern. Fact 8. Gravity gathered matter into knots that would become the first dark halos. Dark matter, invisible to light but felt through gravity, acted as a scaffold in which gas pooled and cooled to form the first luminous objects. This invisible web cradled the first islands of light. Imagine faint scaffolding supporting fragile lanterns in a vast night. Fact 9. The early universe was a simple chemical place, mostly hydrogen and helium. In the first minutes, nuclear reactions made light elements. Heavier elements were locked away until stars forged them much later. Let the simplicity feel restful, like a blank canvas awaiting careful strokes. Fact 10. The first true light comes to us as a record, not as a live broadcast. When telescopes capture ancient photons, they are collecting the scattered souvenirs of long-past eras. Each photon is a messenger from a different time and place, a small, patient traveler. Imagine letters arriving centuries late, every one a quiet story. Now, we drift a little farther toward the first stars, where the first fires began to glow. Fact 11. Recombination is the moment when electrons bound to nuclei and the universe became transparent. This process allowed the cosmic microwave background to travel freely and is often called the universe's first clearing of fog. It left a soft, uniform glow across the heavens. Picture a morning mist thinning to reveal the pale light of a slow sun. Fact 12. The first generation of stars, called population 3 stars, may have been massive and short-lived. Formed from pristine hydrogen and helium, these stars lacked the heavier elements we find in later generations, and they likely burned hot and bright before dying quickly. They seeded space with the first heavy elements. Think of brief, brilliant lanterns that leave faint ash to fertilize new growth. Fact 13. Early galaxies formed as clumps of stars gathered inside dark matter halos. Those infant galaxies were smaller and more irregular than many we see today, merging and growing over time into larger, more ordered systems. Imagine small boats slowly joining into a quiet flotilla on an endless dark sea. Fact 14. The James Webb Space Telescope has begun to show us the light from some of those early galaxies. JWST uses large, cooled mirrors and infrared sensitivity to peer through cosmic redshift and dust, revealing faint, ancient structures that were previously hidden. Its images are like opening a window into a very distant morning. Let this instrument feel like a gentle lantern lifting a curtain. Fact 15. Cosmic reionization was the era when the light from first stars and galaxies ionized surrounding hydrogen again.
Over a few 100 million years, ultraviolet light carved transparent bubbles through neutral gas, gradually making the universe more uniformly lit. It was a slow clearing of a vast, dim sky. Picture small lamps turning on in an enormous dark hall until the room grows politely brighter. Fact 16. Some of the earliest supernovae seeded the cosmos with the first metals. When massive early stars died, their outer layers spread heavier atoms into space, enabling new chemistry and eventual planet formation. That early enrichment set the stage for complexity. Imagine a gentle scattering of glitter that, over eons, allows new textures to appear. Fact 17. Galaxies at high redshift appear redder because their light stretches as space expands. As the universe grows, the wavelength of light lengthens, shifting visible colors toward the infrared. That reddening is a silent signature of cosmic expansion. Think of a soft ribbon being gently pulled, its hue shifting as it drifts. Fact 18. Star formation in early galaxies can be traced by faint emission lines and warm dust. Astronomers read these subtle fingerprints to understand how rapidly stars formed long ago. Those signals are like tiny footprints left in the dust. Allow your attention to follow those small traces, unhurried and curious. Fact 19. The first black holes may have taken shape from the direct collapse of massive gas clouds or from the remnants of early stars. Some black holes grew quickly into heavy seeds at the centers of young galaxies. The exact path is still a subject of careful study, with several plausible routes. Picture a quiet well forming in the center of a clearing, steady and patient. Fact 20. Observations of distant galaxies are always a look back in time. When we point telescopes at faint smudges, we are seeing them as they were billions of years ago. That perspective turns astronomy into a form of gentle history-telling. Let the sense of time slow as you imagine watching an old film rewinding softly. Pause here and breathe. Imagine moonlight on still water, each ripple a thought that eases and then slips away. Fact 21. On the largest scales, matter arranges itself into a cosmic web of filaments and voids. Galaxies and groups trace long, thread-like structures separated by enormous empty regions known as voids. The pattern resembles delicate lace spread across the sky. Picture threads of silver stretching between pools of darkness, patient and vast. Fact 22. Filaments are where most galaxies live and flow, feeding matter into clusters. Gas and galaxies move along these bridges, slowly drawn toward dense nodes where clusters grow. It's a traffic of the cosmos conducted over imaginable timescales. Imagine gentle currents carrying leaves along a wide, slow river. Fact 23. Voids are not completely empty, but they are vast regions with very low density.
These silent expanses can be tens to hundreds of millions of light-years across, with only sparse galaxies drifting within them. They make the web's pattern feel more pronounced. Consider the quiet between chimes in a long, slow bell song. Fact 24. Superclusters group many galaxy clusters into even larger assemblies. Our local region is part of a complex named the Laniakea supercluster, a gravitational basin that collects galaxies into a shared flow. These collections are peaceful on human terms, moving over eons. Imagine a gentle valley where many streams find the same downstream. Fact 25. The Great Attractor is a subtle gravitational pull influencing nearby motion. This region, located beyond many familiar galaxies, affects the peculiar velocities of galaxies in our cosmic neighborhood. It is more of a diffuse tug than a single dramatic entity. Think of it as a faint pull in a wide, quiet ocean current. Fact 26. The dipole repeller is a complementary region that helps shape galaxy flows. Regions of relative emptiness can push matter away, just as overdense regions pull. The interplay of push and pull creates the large-scale motion we observe. Picture two slow breaths in opposite directions, shaping a calm rhythm. Fact 27. Large quasar groups are collections of active galaxies shining across great distances. Quasars are bright central engines in some galaxies, and when many line up, they mark enormous structures visible across a large fraction of the observable universe. Imagine a string of distant lanterns along a ridge, each one calm and steady. Fact 28. Galaxy clusters are enveloped by huge halos of dark matter. Most of a cluster's mass is not in stars, but in an unseen component that holds the cluster together through gravity. Think of a soft, invisible shawl cradling the luminous beads. The presence of this hidden mass is inferred from motion and lensing, not direct light. Fact 29. The cosmic web's patterns emerged from tiny early irregularities amplified by gravity. What began as small variations in density became the skeleton on which complex cosmic architecture grew, a slow and patient shaping over billions of years. Let the long patience of gravity be like a sculptor who never rushes. Fact 30. On the grandest scales, the universe is remarkably uniform, but with gentle variations. If you zoom out far enough, matter and energy appear evenly distributed, yet the subtle texture is exactly what gives rise to all variety. The balance between sameness and difference is quiet and profound. Picture a broad, calm field with a few gentle hills rising here and there. Now drift a little deeper, letting these wide patterns expand in your mind like slow tides. Fact 31. Dark matter interacts primarily through gravity and does not emit light.
We infer its presence because galaxies rotate faster than their visible mass would allow, and because light bends around unseen mass. The exact nature of this component remains one of science's quiet puzzles. Imagine an invisible wind shaping the path of drifting seeds. Fact 32. Dark energy is the name given to the mysterious cause of cosmic acceleration. Observations show the expansion of space is speeding up, and this acceleration is attributed to a property we call dark energy. Its origin and behavior are active topics of gentle, careful inquiry. Picture a slow pressure that gently pushes the fabric of space outward. Fact 33. The relative amounts of dark matter and ordinary matter influence galaxy formation. Where dark matter is denser, gas collects and forms stars more efficiently. Without that scaffolding, galaxies would have taken a different, quieter course. Let the invisible architecture seem like a patient foundation beneath a house. Fact 34. Some dwarf galaxies appear to lack much dark matter, a surprising observation. A few rare systems show motions that suggest little dark matter, and astronomers study them closely to refine their models. These cases are puzzles that invite soft, methodical thinking. Consider them as curious whispers the universe offers to attentive ears. Fact 35. Gravitational lensing lets us map mass even when it's invisible. Mass bends the path of light, so by measuring distorted background images, astronomers can infer where unseen mass lies.
The technique is like reading a hidden map from gentle smudges. Picture a distant candle seen through a rippling glass and all the light it reveals. Fact 36. The cosmic web and the voids between filaments shape how galaxies evolve. Environment matters. Galaxies in dense regions interact more, merging and transforming, while those in quiet voids can stay more isolated and slow to change. Think of city lights and small, remote cottages, each with its own tempo. Fact 37. Ultra-diffuse galaxies can be faint yet surprisingly large. These ghostly systems spread their stars thinly over wide areas and sometimes appear nearly invisible, like fog lit by a distant, weak lamp. Imagine a stadium whose seats are mostly empty, yet its outline still holds. Fact 38. Radio galaxies show us jets and lobes powered by central black holes. Some galaxies emit energetic streams that travel far beyond the visible stars, sculpting the surrounding gas over millions of years. These features are like silent rivers of charged particles. Envision slow ribbons of light unfurling across a vast, dark sheet. Fact 39. Filaments host not only galaxies but also warm gas and magnetic fields. The space between galaxies is not utterly empty. Tenuous matter and weak fields thread the web, contributing to a subtle, diffuse glow in certain wavelengths. Let the idea of hidden texture under the sky be a comforting detail. Fact 40. Cosmic surveys map structure by measuring millions of galaxies across the sky.
Large observational projects trace positions and motions to reveal the web's architecture and its evolution over time. Each new map is a careful, patient portrait. Picture an artist sketching a vast landscape, one quiet stroke at a time. Take a soft breath and imagine threads of light pulling you gently onward, each fact like a bead on a slow-moving string. Fact 41. Stars form in cold, dense clouds called stellar nurseries or molecular clouds. Gravity collects gas and dust into clumps that gradually collapse and heat until nuclear fusion can begin, turning a dark cloud into a bright new sun. Picture a quiet cocoon warming until it softly opens. Fact 42. Protostars are the early, contracting stages before a star fully ignites. During this phase, material falls inward and a central core grows hotter, humming with potential energy until fusion starts. The process can last millions of years for sun-like stars. Imagine a slow ember glowing more steadily as it gathers breath. Fact 43. The mass of a forming star largely determines its path and lifetime. Larger stars burn hotter and exhaust fuel more quickly, while smaller stars like red dwarfs can persist for trillions of years. Mass is the gentle script that sets each star's story. Think of different candles, some small and long-lasting, others brief and brilliant. Fact 44. Nuclear fusion in stars turns hydrogen into helium and in later stages heavier elements. Fusion is the quiet furnace where light nuclei combine to make heavier ones, releasing energy that balances gravity's pull. These inner fires build the chemical richness the universe needs. Envision a steady inner heartbeat that patiently makes the elements. Fact 45. Red dwarfs are the most common stars in the galaxy and burn very slowly. These faint, cool stars can last for trillions of years and are stable companions to their systems. Their unhurried glow is like a calm nightlight. Let the idea of such long-lived embers reassure you with the promise of slow continuity. Fact 46. Massive stars can live short, luminous lives and end as supernovae. When they exhaust their fuel, they shed outer layers and sometimes collapse catastrophically, leaving behind dense remnants and spreading heavier elements. Those remnants glow as nebulae for thousands of years. Picture the slow recycling of material, like leaves returning to enrich the soil. Fact 47. White dwarfs are the cooled cores left by low and medium mass stars. After a star like our Sun sheds its outer layers, the remaining core becomes a dense, slowly cooling object about the size of Earth, but with much more mass. Over extraordinary timescales, it will fade to a black dwarf. Imagine a warm stone gradually losing its heat through eons. Fact 48. Neutron stars are the ultra-dense remnants of massive star collapse. Compressed to a size of just tens of kilometers, they pack more mass than the Sun into a small sphere, and their interiors are a realm of extreme physics we are still learning to describe. Let their density be an abstract wonder rather than an urgent fact. Fact 49. Some neutron stars appear as pulsars, emitting regular beams like lighthouses. Rapid rotation and strong magnetic fields channel emissions into beams that sweep past observers with clock-like regularity. Detecting them is like hearing a distant metronome across the dark. Allow the steady beat to slow your breathing a little more. Fact 50. Supernova remnants can glow for tens of thousands of years after the initial event. The expanding shells of gas and dust interact with surrounding space, producing long-lived nebulae that slowly cool and disperse their elements into the interstellar medium. Picture a lantern's smoke spreading across a vast, slowly moving sky. Imagine now the faint echo of those long-lived nebulae, the soft afterglow that keeps telling the story. Fact 51. Some of the most magnetic objects in the universe are called magnetars. These are a special kind of neutron star whose magnetic fields can be 1,000 trillion times stronger than Earth's, and that field quietly twists and heats the surface, producing X-rays and soft bursts that fade over years. Imagine an invisible, immense compass needle hovering in a cool, distant night. Fact 52. Stellar mass black holes form when very massive stars end their lives and collapse inward. When the core of such a star can no longer resist gravity, it compresses into a point with an event horizon, a boundary beyond which light cannot escape, and the leftover material can spin and glow briefly as it falls in. Picture a deep, silent well whose rim glints for a short, slow while. Fact 53. Supermassive black holes sit at the centers of most large galaxies. These giants weigh millions to billions of times the mass of the Sun and anchor their galaxies with a steady, invisible gravity. Their presence shapes the motions of stars and gas over cosmic generations, like a slow heartbeat at the center of a vast organism. Fact 54. Sagittarius A star, the supermassive black hole at our galaxy center, is a calm but massive neighbor. Located about 26,000 light-years from us, SGR-A star influences the orbits of nearby stars and quietly accretes gas, while long-term observations reveal motion and change on gentle timescales. It is a distant, steady presence to which many small stars are tethered. Fact 55. Near a black hole, time itself can appear to slow compared with faraway clocks. General relativity predicts that strong gravity dilates time, so a watcher close to a heavy object would see distant events speed up, while those far away would see the nearby world move in a different rhythm. Think of two metronomes ticking at slightly different complementary speeds. Fact 56.
Some black holes launch narrow, energetic jets that travel for hundreds of thousands of light-years. These jets, powered by gas spiraling into the center, carry particles and magnetic fields into intergalactic space and sculpt the surroundings over millions of years. Imagine a thin, patient river of light and particles unspooling across a vast, still plane. Fact 57. Gravitational waves are ripples in the fabric of space-time produced by accelerating masses. In 2015, the LIGO Observatory directly detected tiny distortions from merging black holes, confirming a century-old prediction and opening a new, quiet sense organ for the cosmos. Those ripples are like distant, imperceptible breathings that our instruments can now feel. Fact 58. Gravitational waves mergers give off gravitational waves that briefly change space-time itself. When two compact objects spiral together, they radiate energy as waves that stretch and squeeze space for a moment, and those faint signatures travel across the universe until sensitive detectors record them. Picture two dancers converging, their final steps sending a soft shiver through the floor. Fact 59. Some theories suggest primordial black holes might have formed in the early universe. These hypothetical objects could have arisen from density fluctuations in the first fractions of a second, but their existence is still debated and would require careful evidence. Consider them a whisper of possibility at the edge of what we can test. Fact 60. Hawking radiation is a theoretical process by which black holes could slowly evaporate. According to a calculation that blends quantum ideas with gravity, tiny amounts of energy may leak from a black hole over truly vast timescales, making the largest black holes effectively immortal for now, but not necessarily forever. Think of an almost imperceptible sigh that over imaginable eons amounts to change. Fact 61. The Event Horizon Telescope captured the silhouette or shadow of a black hole for the first time. By linking radio telescopes across the Earth into a single virtual dish, the EHT produced an image that showed the dark center framed by glowing gas, giving a calm, indirect view of a region where light bends severely. It felt like finding a distant, dim doorway in a night-lit landscape. Fact 62. Accretion disks are the luminous rings of gas and dust that spiral into compact objects. Friction and compression heat the material, causing it to radiate across wavelengths from radio to X-rays, and the slowly changing glow tells astronomers about dynamics close to the event horizon. Picture a slow whirlpool of gentle light drawing inward. Fact 63. Tidal forces near compact objects can stretch and tear apart stars in rare events.
When a star wanders too close to a massive black hole, gravity can pull it into long streams of gas that feed the center and create a soft, long-lived flare. Imagine a flower caught in a distant tide, its petals drawn out and scattered, leaving new traces in the dark. Fact 64. Some neutron stars show sudden starquakes that release energy in measured bursts. As their crusts adjust or their interiors rearrange, magnetars in particular can emit short, bright pulses that gradually calm, offering a window into dense matter physics that remains quietly mysterious. Think of an old creaking bell that rings briefly and then settles. Fact 65. Cosmic rays are high-energy particles traveling through space and occasionally sparking the upper atmospheres of planets. Originating from energetic processes like supernova remnants and active galactic nuclei, these particles streak across space and leave subtle signatures when they meet matter. Picture faint sparks crossing a quiet, invisible highway. Fact 66. Gravitational wave astronomy gives us a new way to hear events otherwise hidden in light. Merging black holes and neutron stars can be invisible optically, but loud in space-time ripples, and combining wave detections with electromagnetic observations helps us build fuller, gentler stories of those distant meetings. Imagine listening and watching at once, each sense filling in the other's hush. Fact 67. Some neutron star collisions create heavy elements like gold and platinum. When two neutron stars merge, conditions for rapid nuclear reactions briefly appear, forging elements that later spread into space and eventually join planets and perhaps life. Consider the quiet provenance of familiar materials traced back to rare cosmic unions. Fact 68. Relativistic jets sometimes carry enough energy to slow or stop star formation in galaxies. By heating or pushing away surrounding gas over millions of years, these outflows can gently regulate how galaxies grow, serving as a slow thermostat in cosmic development. Picture a subtle wind that curbs the gathering of mist into new clouds. Fact 69. Telltale signatures like emission lines and radio lobes help astronomers identify active galactic nuclei. Careful measurements of light and radio waves let scientists recognize when a galaxy's center is feeding and reshaping its surroundings, a quiet diagnostic that reveals energetic behavior without fanfare. Think of reading the smudge patterns on a long unused window to understand its past. Fact 70. The most extreme compact objects challenge our understanding of matter under pressure. By studying pulsars, magnetars, and the densest neutron stars, physicists probe states of matter that cannot be replicated on Earth, learning new, restrained lessons about nuclear and particle behavior. Allow the sense of disciplined curiosity to wash over this fact like a mild tide.
Take a slow, even breath and imagine the steady hum of instruments listening across decades and continents, gathering soft data like rain into a calm pool. Fact 71. Galaxies rarely stay unchanged. Many grow through slow mergers with others. Over billions of years, collisions and assimilations rearrange stars and gas, sometimes triggering gentle waves of star formation or reshaping disks into larger ellipses. Picture two quiet ships gliding together and eventually becoming one broader vessel. Fact 72. Our Milky Way is a barred spiral galaxy with a disk of stars and a central bulge. It hosts hundreds of billions of stars, swirling in a pattern that feels familiar to us as a broad luminous pathway across the sky. Envision a wide luminous pinwheel turning slowly in the deep. Fact 73. The Andromeda Galaxy is our nearest large galactic neighbor and is on a slow collision course with us. Traveling toward the Milky Way at a modest speed, The two galaxies are expected to meet in about 4 billion years, a long, quiet rearrangement that will unfold on calm cosmic timescales. Imagine two pale clouds drifting together to form a single, softer cloud. Fact 74. The local group is a small family of galaxies that includes the Milky Way and Andromeda. This grouping, bound loosely by gravity, hosts dozens of smaller satellite galaxies that orbit and interact gently with their larger companions. Picture a neighborhood of houses with different yard sizes, each contributing to the local rhythm. Fact 75. Satellite galaxies can be pulled apart by their larger hosts over long periods. Tidal interactions strip stars and gas from smaller systems, leaving streams and faint traces that astronomers can map to reconstruct the past. Think of scattered threads on an ancient tapestry that reveal a former pattern. Fact 76. The Milky Way is surrounded by an extended halo of dark matter and faint stars. This nearly invisible envelope influences the motions of distant satellites and acts as a reservoir that slowly exchanges matter with the galaxy disk. Imagine a faint protective fog that still touches all the outlines below. Fact 77. Radio galaxies and giant lobes can extend far beyond their host galaxies. Emitting primarily at long wavelengths, these sources reveal histories of activity and interaction with the surrounding medium, and are often best seen with radio telescopes. Picture low, slow billows reaching outward like acoustic echoes frozen in space. Fact 78. Galaxy clusters can contain thousands of galaxies and a hot X-ray emitting gas between them. The intracluster medium is a diffuse, warm plasma that glows softly in high-energy light and shapes how galaxies behave in dense environments. Think of a shallow, warm mist bathing many islands of starlight. Fact 79. Over very long timescales, galaxy clusters can merge to form even larger structures.
These slow events alter the trajectories and environments of member galaxies, building the cosmic architecture in gradual, patient steps. Imagine river deltas merging into larger plains over ages we cannot easily imagine. Fact 80. The Virgo supercluster is part of an even larger arrangement that includes Laniakea. These labels describe our place in a vast nested set of structures where gravity subtly organizes matter into coherent flowing networks. Let the idea of belonging to layered neighborhoods be quietly reassuring. Now, let your thoughts drift among these galaxies as if watching gentle lanterns along a vast shoreline. Fact 81. Thousands of exoplanets have been discovered orbiting other stars with a large diversity of types. From small, rocky worlds to giant gas envelopes, these planets show that planetary systems come in many configurations, each with its own slow story. Picture a panoply of dim, patient jewels scattered around distant suns. Fact 82. Some exoplanets are tidally locked, keeping the same face toward their star. On such worlds, one side basks in perpetual day, while the other stays in long night, creating stark but stable climate contrasts that could allow narrow habitable zones along the terminator. Imagine a slowly warmed hemisphere and a cool, restful opposite. Fact 83. Lava worlds are planets so close to their stars that their surfaces may be molten. These extreme, radiant places glow with heat and may sprout vaporized rock atmospheres, yet they exist quietly at a steady, fiery calm in their narrow orbits. Picture a distant, slow ember spinning faithfully around its light. Fact 84. Ocean worlds may hide global seas beneath thick ice shells. Moons and planets in our own and other systems could host subsurface oceans, where heat from tides or radioactivity keeps water liquid for eons, creating environments of gentle, hidden motion. Think of silent blue depths under a glassy, frozen roof. Fact 85. Some planets may experience diamond rain when extreme pressures turn lighter elements into crystals deep in their atmospheres. On certain large, carbon-rich worlds, high pressure and temperature can compress carbon into solid forms that fall inward, a slow, exotic weather that rearranges interior layers. Imagine glittering flakes drifting steadily toward a dim core. Fact 86. Rogue planets wander the galaxy untethered to any star. Ejected from their birth systems or formed in isolation, these lonely worlds travel through interstellar space, cold and slow, lit only faintly by residual heat or cosmic background light. Picture a small, dark pebble drifting through a vast pool. Fact 87. Circumbinary planets orbit two stars and experience unique patterns of light. These worlds circle a pair of suns, leading to shifting day-night cycles and complex climates that evolve on long timescales. Imagine two distant lights rising and falling in a dreamy, intertwined ballet. Fact 88.
The search for biosignatures focuses on gentle chemical imprints in planetary atmospheres. By measuring specific gases and their ratios, astronomers cautiously look for signs that lifelike chemistry may be present, always with caveats and careful modeling. Let the idea of patient detection be like watching for a faint, steady glow at the edge of a shoreline. Breathe in slowly and picture these distant worlds turning, each with its own slow weather and quiet seasons. Fact 89. The concept of the universe's heat death describes a distant future of maximal entropy. If expansion continues and energy spreads evenly, usable energy differences will dwindle, and processes that sustain structure will peter out over unimaginable timescales. Imagine a long, calm evening stretching into a gentle, featureless dusk. Fact 90. Black holes may persist far longer than stars, but could eventually evaporate via Hawking radiation in theory. On timescales vastly longer than the current age of the universe, microscopic quantum processes might cause black holes to lose mass slowly, a quiet fade that is speculative but mathematically suggested. Picture a single tiny spark, taking eons to wink away. Fact 91. White dwarfs will cool into black dwarfs over extremely long, slow periods. After a sun-like star ends nuclear fusion, its warm core radiates away heat for trillions of years until it becomes an inert, dark object, a far future stone in cosmic terms. Let that patient cooling feel like the settling of a long-used hearthstone. Fact 92. The possibility of proton decay is a hypothetical idea that would slowly erase matter. If protons are unstable over incomprehensibly long timescales, ordinary atoms could eventually decay, but this remains an unproven and cautious area of study with no current confirmation. Consider it a quiet theoretical murmur about the deepest stability of matter. Fact 93. Cosmic expansion may drive galaxies away from one another, isolating future observers. As space grows, distant galaxies can cross horizons and recede beyond view, meaning future local skies might be dominated by a single merged system. Imagine islands drifting apart until only a familiar shore remains. Fact 94. The fate of the universe depends on dark energy's behavior, which remains uncertain. If the property driving acceleration changes over time, scenarios range from gentle continued expansion to more exotic possibilities, but current observations suggest a steady, slow acceleration. Hold the uncertainty like a soft, unresolved chord. Fact 95. Long-term astrophysical processes play out on timescales that can be soothing to contemplate. Thinking in billions and trillions of years reframes daily anxieties into a vast, slow narrative where many things simply take time to unfold. Let this shifting scale ease your sense of hurry as you rest. Now, let the idea of these immense timescales cradle your thoughts, like slow ocean swells rocking a small boat. Fact 96.
The atoms in your body were forged in stars through nuclear fusion and stellar explosions. Elements heavier than hydrogen and helium were created inside generations of stars and dispersed by winds and supernovae, later becoming part of planets and living things. Think of your material self as a quiet heirloom handed down across cosmic seasons. Fact 97. We are, in a meaningful sense, the universe becoming aware of itself. Through consciousness and curiosity, matter arranged into minds that can study the cosmos, creating a gentle loop of self-observation that is both humbling and consoling. Imagine the universe reading its own faint handwriting in soft, patient script. Fact 98. Human instruments like JWST, LIGO, and the EHT are delicate windows into distant truths. Each observatory extends our quiet senses. JWST peers in infrared to reveal ancient light. LIGO listens for spacetime's subtle vibrations, and the EHT stitches telescopes together to reveal shadowed silhouettes. Together, they represent a calm, collective attention reaching outward. Fact 99. Looking outward to the cosmos can bring a comforting sense of perspective. Realizing how small and connected our world is within a vast, gently moving universe often invites humility and a softened heart, an unhurried consolation that our troubles are part of a much broader story. Let that perspective be a quiet companion as you let go. Fact 100. The universe keeps its patient rhythms long after our short days, and that steadiness can lull us toward rest. From the slow cooling of stars to the quiet drift of galaxies, cosmic timescales remind us that much is gradual, cyclical, and expansive. Imagine lying beneath an immense dim dome, where every small thought is folded into a wider, calm pattern. If this evening's calm stayed with you, a like or subscription helps bring more sleepy journeys. Good night.